Building Green. And I interviewed all three of our presenters while I was writing a feature article recently on the topic of designing for anticipated changes in temperature and humidity that might affect building performance. This is an opportunity for you to get a deeper look at the research that these three are doing and how it applies to your work. Okay, so first some quick introductions to our expert and very busy guests who have graciously agreed to join us today. Russ Jones, who will be speaking first, is a managing analyst at climate consulting company Stratus Consulting, where he has worked on a wide variety of projects, including studies modeling impacts from sea level rise and storm surge. He'll be talking to us today about the state of climate science and how climate modeling is done. Chuck Keown is co-founder and executive vice president of Weather Analytics, which collects and customizes weather data to help companies and government agencies in their analytics and planning. Chuck has extensive experience in the design and construction sector as well, and he currently serves on the ASHRAE Climate Committee. He'll be talking today about new types of weather files that his company is developing to help with energy modeling and other design tools. And finally, Christoph Reinhardt is an associate professor in building technology at MIT, where he heads the Sustainable Design Lab. He has particular expertise in daylighting, passive climatization techniques, and the influence of occupant behavior on building energy use. And he'll be sharing with us his research on the potential performance effects and economic repercussions of climate change for designers as well as building owners. Okay, so with that, I'll turn it over to Russ Jones of Stratus Consulting.
Hi, everyone. I'm going to just give kind of a very brief overview of some of the climate change variables that we examine and the uncertainty surrounding them. And I'm going to start off with my talk with a basic assumption that climate change is real and that it is human influenced. And I know there's a lot of people that don't feel that way, but if you look at the climate record, it's pretty clear. You can see in this graph of observed change in global mean temperature from 1850 to about 2010. On the top half of that graph, average annual change in temperature has been rising steadily. And even if you look at the decadal averages, there's been a lot of talk from people saying, oh, the last 10 years have been flat, we're not seeing anything. You can still see that it's been increasing even if you look at those decadal averages. If we move on to sea level rise, same thing. Multiple data sets are represented in different colors here. You can see from 1900 through 2010, a pretty steady increase in sea level rise. So, climate change really is happening. I believe it's anthropogenically caused. Most of the scientists in the world also believe that. But there's a lot less uncertainty in terms of what are the future projections. How is climate going to be changing? And there's a lot of uncertainty around this at many, many different levels. There's uncertainty on the emissions scenarios. How much greenhouse gases are China and India going to be emitting, or are they going to go green? There's uncertainty in global circulation models. So there's many centers from scientific centers around the world that have put together climate change models, but they model the circulation differently. Spatial scale, whether you're looking at a very near term versus 50 years out, 100 years out, there's a lot of uncertainty in that. The variable examined, there's quite a bit of certainty in terms of how much sea level rise is going to be going up, but much less when it comes to like precipitation. And then as Chuck is going to talk about later, in baseline data, there's a lot of variability in the baseline data, whether you're taking averages over an area, whether you're looking at a site-specific location, that type of thing. And I should mention that all these are additive. So these uncertainties build on each other. So in terms of spatial scale, there's a range of projections at every spatial scale. On the global scale, the uncertainty really comes around from the emission scenario, whether, China is going to be exploding or not. And in addition to that, how much the temperature goes up when you double the CO2 or other greenhouse gases. And then at the regional, local, and site-specific scales, you also get, a lot of variability just because these global models don't really take into account a lot of the local processes, the topography, or in a local setting, which side of a lake you're on, or in a site-specific, maybe there's a heat urban island effect. So each scale has its own set of uncertainties, and this increases with the higher the resolution. And I've kind of gone over those last 2 points there. The climate variables examined. So as I mentioned, there's a lot more certainty in terms of temperature than there is in precipitation. But also in terms of the type of event. Are you looking at, long-term averages, or are you looking at extreme events? This kind of goes at, well, what's important in terms of building? Are you interested in looking at the average annual changes in maximum, minimum, or mean temperatures, or are you more interested in looking at that 24-hour maximum event? Also, the length of the event. Maybe it's something like the number of days above 95 degrees Fahrenheit that you're interested in, or the average number of days without precipitation. So these length of events are also important. And also the recurrence of a threshold event. So maybe it's really that 100 or 500 year flood or heat event that you're interested in, and you're curious to see, well, how is that going to be changing in the future? So how we handle climate change uncertainty, you really need to answer questions that are pertinent to the need that you have. What is it that makes a difference in terms of buildings? What are the variables that are important? Is it that threshold event, or is it the long-term averages? And what kinds of risks are you willing to live with? Are you willing to say, well, most of the time we're going to see climate change, in this way, but we're not really all that concerned about those outliers? Or maybe it's, no, it's really those big events. Living here in Boulder, we had the big floods this year. That was a watershed event that we were very concerned about. What is the time frame that's important to you? Is it, you're looking 1 year out, 10 years out, 20 years out, 100 years out? Need to keep that in mind. And then, how important is the site-specific location? Are you interested in, designing buildings that, for one specific location, or are you more interested in the regional area? So we can, so that's one way to answer, kind of get a grasp on the uncertainty. Another way here is to pick GCMs that do a better job historically in your area. So some climate models will do well in, say, one part of the country, but not well in another part. So you can kind of hone in on getting a possibly better estimate looking historically at how that model has done in your area. But you do have to keep in mind that just because a model did well historically doesn't necessarily mean that it will, project the future equally as well. Another way to handle uncertainty is to examine the range of climate outputs and to bound your estimates. So in this case, maybe you pick a a high emissions scenario with a really hot, dry model, and you look at that one. You also pick another one that's a cool, wet scenario, and maybe a middle of the road scenario, so that you try to bound what is the range of uncertainty that I'm going to be looking at. And that allows you to know the potential range of the outcomes. Another common technique that people use is to take averages across a variety of models. And these seem to do quite well in terms of hindcast in projecting past climate. But a couple issues. One, as I mentioned, it's necessarily an indication that will show you what's going to happen in the future. But the other problem is that when you take these averages, it may dampen those tails. So you may not get those extreme events, which could be important to you. And then a third approach is to examine the number of models in agreement. So maybe you're interested, you're not so interested in those extremes, but you want to say, well, what do the majority of the models say, or what do 2/3 of the models say? So in conclusion, as I mentioned, there's a ton of uncertainty in terms of climate modeling, from emissions, model output, spatial scales, and temporal scales. But really what you need to do is simplify for the variables that are important to you over what time period, and really, really the level of risk that you're willing to take. And that will help you, figure out the types of analysis that you want to do to show you those ranges. And there's a variety of websites out there and applications to help you do this type of analysis. They will put together ensembles or individual model scenarios at different emission scenarios. So I encourage everyone to check those out. And now I'm going to turn it over to Chuck.
Thank you, Russ. I'm going to move this. We're with a private company, although we do a lot of our own research, and we're focusing on a number of things. But in the case here, the problem that Russ actually outlined was that while global climate models are, they can add an awful value, the more you want to assess the impact on a particular site, the higher the resolution, the more difficult it is to use these, the output of these models. The trouble is, of course, that design decisions almost always are local. Okay, they are site or small area specific, and they can't. And while the climate is changing, okay, and you actually can't wait on making decisions. You have to find the best way possible to make decisions on how you're going to handle or even estimate what the heating and cooling loads are going to be in the future, and in some cases, even more important, what about the increased frequency and severity of extreme weather events? What we've been working on since 2009 is we've basically been working on essentially digitizing the entire global atmosphere back now 34 years. Okay, we've pulled in the best that we could find of all the satellite remote sense data, all the observed data from the ground stations, plus the model sources that output gridded historical data and gridded forecast data. We have over 580 variables, full coverage from actually about 4 meters below the surface of the Earth to the top of the stratosphere, and we've mapped those into 650,000 geostable grid areas, and then spent the effort to clean, rationalize, filter, and stabilize everything so that all the variables are consistent, and so that it is a statistically stable database representing every hour from early 1979 through 7 days ahead for each one of these grid squares. Then we keep it up to date. Every hour we pull in all the ground station observations, and every 6 hours all the new modeled output from NOAA. And we've got it all spinning in a cloud database. It is basically designed to take the randomness, the errors, and the sort of esoteric strangeness out of weather data, so you can start putting it into analytic engines and help make some decisions that are useful. We have built some sort of offerings right now that can help this getting a handle on the impact of the changing climate. If you have your own ability to do analysis, you can get 34 years of gap-free data anywhere in the world. It's consistent, and it's consistent place to place. So if you do an analysis in one part of the world, it will be statistically valid in another. And we have that data not only every hour, but also daily averages, mins, max, sums. We even have daytime, nighttime, month, year data to support analyses. We have built for the energy modeling community on-demand TMY files that are always up to date through the end of the last year. And we've given the options to do them for 30, 15, 10, or the last 7 years. And we're working with a couple of companies to analyze the difference of looking at the typical weather for the last 7 years against the typical weather for the last 30 years and finding some non-insignificant changes. So we're trying to provide those options. We also have the hard-to-find variables, solar radiation, soil moisture, soil temperature, snowfall, ice, freezing rain, and the like. Solar radiation being an important one for, instead of having it be estimated from cloud cover, we have the actual solar radiation. What's more interesting is the stuff that we're working on, okay? We are, because we build TMY files on demand, we are altering the algorithms that produce them so that we will soon have what we call extreme meteorological year files. In other words, over the last 7 or 10 or 15 years, what were the coldest set of months on record, or the warmest set of months on record for that location, or the wettest, for example. We have an algorithm for in urban areas for converting the typical meteorological year to urban, and as we work down a few points on this slide, as we are working on looking at trending for any variable over the last 34 years, we have the basis for providing future meteorological year files, which would be applying the trends within limits, and then taking the temperature and humidity and the like out 10 or 20 years. We are also downscaling this is the grid system we have right now is 35 by 35 kilometers. We are downscaling eventually it'll be the entire landmass, but right now we're starting with the U.S. and working on severe events so that you have the data down to 1 kilometer, which is particularly important for measuring the frequency and intensity of severe events. We're also working on the trending that I mentioned, where you look at for any variable what the probabilities are for particular extreme events, and how are those probabilities changing over time, and looking at the frequency analysis for severe events. It is very good to have 34 years of data. It is, in some cases, it's always be better to have 100 or 150 years of data in case of those very large storms. You have to have them in the data set for it to be statistically represented. That said, what we're trying to do is come up with an additional set of tools to augment the global climate models and other catastrophic models and the like that are out there now that are based on modeling the atmosphere with kind of a bottom-up approach that says you also should look at what are the exact trends at a particular location, and use both pieces of data in order to make your decision. These are just a few examples. I just picked Gloucester, Massachusetts to show over the last 30 years that the air temperature is getting slightly warmer there, but it's getting the precipitation rate is actually increasing at a higher rate, including the maximum single-hour precipitation. I think the next slide is just the frequency. This one's even more interesting. If you look at the frequency of rain events in Gloucester over 2.5 inches or 2.25 inches of precipitation in a given day, it only happened 3 times in the 80s. It happened 5 times in the 1990s. It happened 13 times since 2000, and it's that's the sort of thing that is coming out of our data. And then finally, we're doing these decade by decade comparisons of what are the probabilities to aid the decisions and the design decisions and the like. In this case, it's the same location. What's the probability of over 65 inches of annual rainfall? In the 80s, it was only 0.5%, and it's gone all the way up to 2.1% likelihood of that much rainfall after in the decade starting with 2000. So that's just the base set of tools that we're working on to try to leverage the data, and we're always looking for people to work with that that want to leverage the data and make some tools that enable making conclusions out of it. So that's that. I would like to now turn it over to Christoph Reinhardt for his presentation.
Good morning or good afternoon, depending on where you are. Thank you for joining us today. So after Russ gave you a bit of a background of the different general circulation models that exist that we are using to predict climate change, and Jacques talked about the different ways of how we are generating weather files, I am now going to talk about actually the application of these models in design. So and for that, I'm going to give you several examples of where we've worked with climate change data for building design at the Sustainable Design Lab at MIT. Okay, so as I said, you've seen all these graphs before, general circulation models. These are different GCMs that are predicting how the world global temperature is going to change over the next 80, 90 to 100 years. So now, how can we use these type of models for actual climate design? And there is a method out there that is called morphing, and the way it works, it basically, it was developed by Drew Crawley and others. What it does, it uses your TMY or EPW file that you're using. So basically, we have methods out there that use the IPCC global circulation data and then combine it with a weather file that you're using for your site, and that helps you effectively to create a new climate file. So specifically, if you go to this website that you're seeing here, the Climate Change Weather File Generator from the University of Southampton, it's an Excel-based file that you see here, a screenshot on it. You are basically able to load in an EPW file from whatever site you want to work in, and then you are selecting for what future scenario you want to generate a climate file, and then you get a new TMY3 file. So what you're doing with this, how large is this effect? Here you see an application of where we use a TMY3 file for the Graduate School of Design at Harvard. That's the architecture school. So on the left, you see the building. On the right-hand side, you see a design builder model, which is a software based on Energy Plus. And what you see here is monthly predicted, so simulated and measured energy use for heating and cooling the building. And the main point is here, if we do that for 2009, 2010, we are getting very good agreement. So our model actually works. If we are now using the climate data for 2018 according to the IPCC A2 scenario, which is a middle of the line scenario, then actually the same building in Boston will use 36% less energy over the whole year for heating and 45% more energy for cooling. So it's a really dramatic effect. And for those of you that are interested in doing sustainable building design, designing buildings for the future, it's obviously necessary that we start taking this into account as well. So once we looked at the effect of how big it can be, let's look at how we can apply it effectively. So one question that we looked at here was basically to see, well, if we are designing a building for comfort, for natural ventilation now, how comfortable is this building going to be according to the ASHRAE standard 55 in, let's say, 50 years or so? And in order to use a case study, what we've done, we worked with this project here located in New York, where a new complex was these buildings that you see here, these high-rise buildings, were supposed to be designed next to a low-income housing facility close to LaGuardia Airport. And the first thing, of course, you notice when you put up this massive new infrastructure here, that these new buildings here are going to block the sun for the existing buildings, and they're also going to block the wind. So if we do just a simple wind analysis with the new buildings here, well, first of all, just due to the effect that the climate is warmer, the good news is actually that the heating in the heating season, because the climate is more temperate, we actually get reduced solar radiation on the building. The overall effect is that we increase our heating demand by about $900 for a unit here in this low-income housing scenario. If we look at the wind situation, what you actually see doing that is being used in these buildings during the summer, that the new buildings are blocking the wind effectively. So we get a lot less natural ventilation potential in these low-income housing high-rises. And if you realize that right now most of these buildings don't have air conditioning, we can now look at what does this actually mean going forward. So this is what this graph effectively summarizes. So what you see in blue is the temperature distribution within the place if we have air conditioning. And of course, it doesn't matter what climate we have. If we have reliably working window unit air conditioning in the system, we can get the hours of the year when the building overheats under control. What we also see in the current situation here, we have about 25% of the time when people are in the building right now, we will have overheating over 80 degrees Fahrenheit within that building. But if we now look at the future climate scenario, we actually see that this number greatly increases. So if we put these effects together, what effectively is going to happen is that if we only had climate change and no change in behavior, then since the climate is getting warmer, the heating energy in the buildings will be reduced. But if they don't purchase any air conditioning in these units, the electricity use is going to stay the same, so we would save energy. But actually, of course, what's going to happen, since the building will be overheating so dramatically, there will be more air conditioning, so we actually overall need 25% more energy for the fuel costs. So this gives you a sense of how you could apply this type of future climate files for a thermal comfort study looking forward. Another example that I wanted to say is just a combination of climate change and money. So this is a study that we've done where we looked at not only for different climate change scenarios and how far the climate is going to change, but also what the US government is predicting, what the retail prices for these different scenarios are going to be. And what we actually finding is, this is a method, this is a paper done by Seth Holmes and myself. What we are finding there, actually using these predictions of future energy prices, we can basically now tell you not only how much energy a building is going to use going into the future, but also how much it's going to cost you to maintain for energy use in these buildings. So this is our little case study. Imagine you have a building located in Boston. In the top case, it's just a 1980s office building, and the baseline is the owner doesn't do anything. 5,000 square meter, we keep the building as it is. And now let's assume we're bringing it up to code. The cost would be about $90,000. If instead we go for a more aggressive scenario, adding mixed mode ventilation, solar shading, the costs obviously go up. So now we want to do analysis, how much is this going to cost us? And what you're going to see in this slide actually here is for this case study located either in Boston or in Phoenix, different scenarios. So if this is the baseline, the building is going to cost us between 2010 and 2080, just under $2 million in operational cost if we don't consider climate change. This number is going to go up to $3 million depending on what climate scenario we are using if climate change and future energy prices are going to be taken into account. So what you see here in the case we don't do anything to the building, the costs are going to be highest, whereas when we do medium, minimum, or advanced upgrades to the building, the costs of the building are going to go down. But what's also very interesting is that the uncertainty, since we obviously don't know today what climate change what kind of future the future is going to bring to us, what kinds of climate change, you see that if we do more resilient buildings, the uncertainty goes down. So this is certainly an argument why building green building is a good idea. If instead of in Boston, we're doing the same type of analysis for a building that's located in Phoenix, so you see that the effect is a lot larger, because if the climate is getting warmer, in Phoenix we are only in the cooling mode, so the effect is just a lot bigger. So this effectively gives you a method here in place that allows you to basically combine climate change with future energy prices, and that in turn allows you then to justify the costs of building green. And this is an analysis where instead of looking at the overall cost, we're looking at the payback time. So here you see basically for these different medium, minimum, and advanced upgrades, what the internal rate of return is. So am I going to invest this money into a retrofit or not? And what you see is effectively that unfortunately just bringing a building up to code actually has the biggest bang for your buck, so to speak, and the reason for this is that energy prices, even the predicted ones, are just too low right now in our country. So this is a little study that I quickly wanted to touch upon. This more goes into the idea of architectural design. So there is right now obviously a trend that we try to optimize our building that is as climate responsive as possible. But how do we do that if we actually have climate change upon us? So what you are seeing here is just an example of this type of trend. This is from the SOM Black Box Studio, where they basically came up with this very complex, intricate looking skyscraper, and they said due to radiation map optimization, this is the best type of building form. So we basically wanted to take this analysis further and do the analysis for different climate scenarios. So if you're doing that, what we've done, a simulation study using a very simple space, and all we are changing are insulation levels in the walls, window to wall ratio, and the overhang depth. And then we use an optimization algorithm to basically come up with what is the best facade for a different climate. So here in summary, we did this analysis for single spaces facing in the 4 cardinal directions in Boston, Fairbanks, and Phoenix. And we either said, let's do the analysis using our current climate, 2020, 2050, 2080, or over a long period. And of course, when you do this analysis, you have to do the choice. Do I want to optimize my costs? So do I want to optimize over 10 years the energy costs for my building, or do I want to optimize carbon emissions? And when I'm optimizing carbon emissions, then I'm weighing cooling a lot more, so I get different solutions. And here you just get a snapshot of our results for a south-facing space in Boston, Massachusetts. Effectively, at the top, what you're seeing here, I have a pretty small 30% window to wall ratio window and R10 wall. That's the best bang for my buck if I'm designing for now. That pretty much doesn't change so much. As the climate gets hotter, I get slightly better insulation levels. But if I do a long-term analysis, so I analyze between 2020 and 2080, then actually a larger window actually with a bigger R value gets the best results. And if I'm, instead of doing a cost optimization, a carbon analysis, you see you have an overhang that's that's slowly growing as it gets warmer and warmer. So the last point that I quickly wanted to bring across is just this notion: how do we basically optimize not only for embodied energy, not only for operational energy, but also for embodied energy over a long lifespan. So we've started basically with this technique to model either neighborhoods or individual buildings over the next 80 or 100 years. So what happens then, as you take climate change into account, you see that the annual energy cost for operation is slowly falling because the climate is getting warmer, and at the same time operational energy is getting higher. And this is some of our latest work where we are effectively trying to weigh the two against each other. And if you are applying this, what you're seeing is that often partly retrofit is actually saving you more than basically just demolitioning buildings and building new buildings overall. That's what I had for this presentation. Oh, I see here. Yeah, the scales are different. Basically, we've done this is a mixed up set of slides. What we've been what we've been using, what you obviously want to do, you want to add the operational and the embodied energy together, and then you see basically when the two lines come together, and that gives you kind of an idea whether retrofitting a building or building a new building, whether the embodied energy within that new building stock is more than in the case of just looking at operational energy.
Great. Thank you so much again, Russ, Chuck, and Christoph. So here is some email information for each of them if you have kind of some deeper questions that you wanted to discuss with them. So now I wanted to go to the questions. We've gotten a few good questions and comments so far. First, I wanted to ask, when Russ was talking, he mentioned GCM, and we heard from Chuck that stands for Global Climate Model. Sorry, that wasn't clear. But also then we got a follow-up to that. If somebody said it's also described as Global Circulation Model. So Russ, I'm wondering if you can speak to whether there's a difference between those two things.
No, it's just terminology. It can also be General Circulation Model as well. So depending on who you're talking to, people will use different terms.
Okay. And can you just tell people briefly what that means?
Yeah, so what these are is they're complex models that try to look at the interaction between the atmosphere, in some cases the oceans as well, and just model how, heating patterns around the world and how that changes the circulation patterns and how that manifests itself in terms of the climate. So when we're heating different areas or when we have different emission scenarios in the atmosphere, how much heat is going to be trapped, how much is going to be let out, how that's going to manifest itself on the surface.
Thank you. Okay, so guys, keep putting your questions into the chat if you need to. I'm going to go ahead with some more that we got. Russ, again from you, somebody was asking if we could get a list of the recommended sites. You did mention that they're free, and I'm wondering if you could send those to me, and then I could either, maybe we could just put them in the chat right now if people want them, or we could send out a list.
I'll need to send you out a list of those. I don't have them off the top of my head, but there are several sites. NOAA's got some. I can send those out to you and you can distribute them.
Great, thank you. So if anybody needs those lists, please write to me at paula@buildinggreen.com and I can send that to you. And then also I wanted to mention, somebody had asked about seeing the slides afterward, and those will be posted online as a PDF, and it'll be a video. But if you do need the slides right away, you can write to me and I can just, send you a PDF of them. Okay, so then we had another question for Chuck. How much of the 34-year data is interpolated? I imagine that there isn't a data collection site in every spot of the globe, so perhaps this is coming from satellite data. Chuck, could you explain where that data comes from?
Yes, I can. It's there is actually no interpolation done. One of the difficulties of weather data availabilities has always been just what's observed, and then people try to extrapolate and interpolate weather stations, some of which can be quite a ways apart and at different altitudes. The data in between the weather stations is based on a new gridded historical data set released by NOAA in spring of 2011 and kept up to date every 6 hours. It is the baseline. It's called the Climate Forecast System Reanalysis Database. It is the baseline, statistically stable, complete view of the Earth's atmosphere that they need as input into their medium and long range forecasting systems. It has to have a statistically stable, at least 30-year rolling base. We have taken that data and downloaded it and processed it, which is quite a job, and then we keep it up to date. And so the spaces in between the weather stations represent the integration of the NOAA model as well as all the satellite observations. To take one step further, the way they build this reanalysis data is they take the same model they use for their forecast system, but instead of running it open loop forward, they go back in time and they run it constrained with as many satellite observations as well as balloons and buoys and the like around the globe, so that it tends to squeeze the error out of its modeling, because all the data has to come within stuff that's been measured. And then they reset that, rerun it every 6 hours from January 79 through right now, actually. So it makes a very good base, and although it represents the average weather across the 35-kilometer grid. But knowing that is still very valuable. I hope that answers the question.
Thank you, Chuck. We did have a question about, it says, it seems like this information is going to make people increase the capacity of their cooling equipment. And I think this came up while you were talking, Christoph. And then a follow-up to that, maybe that's not even necessary since HVAC is typically oversized now. I just wondered if you could speak to that, Christoph.
Yeah, I think the effect on the HVAC equipment capacity, the peak load, is not as big. And actually, in that paper in Building Research Information that I'm happy to send to anybody who sends me an email, shows that this is a relatively small effect. It mostly has to do with that you just need to run your equipment more often. The big effect is, of course, the moment when we want to have a naturally ventilated building. If we implement a strategy today, is that still going to work? And there's some interesting work coming out of England where this is a more common scenario, that natural ventilation in office buildings is being used. And they are now basically based on future climate change scenario analysis, putting in basically provisions so that you can switch from purely naturally ventilated to a hybrid approach. And that's something that you would encounter probably if you were to design today in the Bay Area as well.
Great, thank you. So another question here, it would seem that for long-term planning, our attention should be on greenhouse gas emissions rather than on energy efficiency. Anybody want to take that one on?
Yeah, I agree. I mean, it's ultimately a value system. I mean, we try to always do an analysis and exercises both for money, so cost of energy over a long period, as well as greenhouse gas emissions. And of course, it's easier to convince an owner to when you work in dollars than in greenhouse gas emissions. But long term, obviously, this is where we have to go.
Thank you. Canon Design is wondering, is any of this thinking making it into the codes and regulations that are being revised right now for the future?
I'm on the ASHRAE Climate Committee, and it's I guess the simple answer is not fast enough. It's hard when you're a standards organization who has built up years and years and years of mechanisms to make sure you're making the right decision and to be careful and thoughtful and slow moving. It's hard to respond to a climate that's changing quite as fast as the one that is now. The awareness is growing. The difficulty of changing standards is high because it ripples through so many different legal and semi-legal and political documents and the like, and it's more the thinking at the Climate Committee to try to give people as many tools as possible to augment what the Design 2 conditions say, so that they can make some of their own intelligent decisions.
Thank you, Chuck. Great.
I would actually add one thing to that. I think it's important in order for this to get into the different codes. If you look at what happened in England, there the government basically decided that the most likely future scenario is the A2 scenario, which is kind of a middle of a line development scenario within climate within the global circulation model for the different storylines. You need that. Officially, the IPCC says all futures have the same likeliness, and if you have to deal with that, then you have to basically do an analysis for many different futures. But if ASHRAE or somebody would say we are assuming a certain future is more likely than another, then based on that you can do the type of analysis that we showed.
Well, I certainly agree with you. But it's as standards. It's rare to have a standards organization take a lead on something like that. But we'll keep working on it.
So what we need is more political will, possibly. So
Yes.
there was a follow-up to that. Somebody asking if anybody could comment specifically on the effectiveness of 90.1 2010 in regard to these issues, if I'm understanding the question correctly. Did you have anything on that, Chuck? Just, I know that they did.
No, it's the I think the standards, you should not look to the ASHRAE standards to drive this solution. They're going to follow, in my opinion, not lead.
Thank you, Chuck. So then we had a comment, the more insulation you can incorporate into your envelope, the better safeguards you will have against both extremes in weather, whether hot or cold. Would the panelists agree with this logic?
Yes, you definitely. If you look at the analysis of different design optimization that I showed, then effectively only if you take a long-term perspective and you optimize for 2010 till 2080, then you see that the insulation levels go up. The problem is just the cost of insulation and energy, and that if you just optimize for 10 years, you end up with a more normal wall than if you have a longer time frame. But better insulation is a good climate change resiliency design approach.
Great, thank you. And that's definitely affirming for a lot of the work that the firms who are participating in this webcast are doing, for sure. So here's one that I would like to end on, I think, unless we have time for more afterward. Someone said, I had more questions, but this was a complex presentation. What is the takeaway message? And maybe we could just go from Russ to Chuck to Christoph about, you know, take 1 minute and say what you think is the takeaway message for the building and design community.
Yeah. So my takeaway is kind of what I had in my concluding slide there, that, you know, there's lots of uncertainty in the climate change projections. You know, the trends right now seem to be, you know, what we were thinking 5-10 years ago is our worst case scenario is now our business as usual. You know, we're not making any progress, but there is still a lot of uncertainty. There's a lot of different models and tools out there, but you really just need to know, you know, what is it that is going to make a difference for you, and how can you bound those estimates to see, you know, what would give you an idea as to how best to plan for your design.
Yeah, I echo what Russ says. It's the you can't walk away from the problem. That it's not going to get solved for you in the standards anytime soon. So you have to come up with your own solution. And I would avail myself of as many tools as possible. The best, in general, the best approaches we've seen are people that do their design based on a current, typical year file, and then find one way or another to compare it against extremes. How does it do if it gets really cold? How does it do if it gets really warm? And then make some decisions based on how well they have done. I think that as time goes by, these climate models are going to get even better in terms of the sort of stuff that Christoph showed, that you can run it against a future climate year as well. But you got to check all the things and take your best cut at it.
My main takeaway is I think tools such as the climate change weather file generator that I pointed out are available today. So if you're already doing energy modeling today and you're spending a lot of time building a model, then just downloading the program and just for fun, literally modeling your building in 2080 and see what's going to happen. I think that is a very valuable exercise that you can do today. I think it's a great opener to talk about with your client of what the future might hold. And then there's, of course, the notion both of comfort. Is this building still going to be comfortable? And what are the implications for energy? And I think in both cases, doing this analysis with really, really very limited extra effort opens a new discussion that you wouldn't have had before.
Great. Thank you all so much. I do see a couple more questions that we might be able to answer quickly. Here's a good one for Russ. Is every spot on the planet warming? And how do we find spots that might be cooling or getting wetter, and where can we find that data?
That's an interesting question. I don't know whether there are any spots that would be cooling. I would imagine so. You know, anytime that you heat one part of the Earth, you know, anytime you're changing the heating and cooling of the Earth, you're changing the patterns. And, you know, we've seen some of this stuff with like this polar vortex coming down. There's some thought that what we're seeing is a result of changing circulation patterns from different heating and cooling from climate change. But that's still a research topic. It's not, you know, that hasn't been established yet. But certainly there are some areas that are getting wetter. There's a lot of areas that are getting drier. So it's really, you know, just it's place dependent where you are. And there's a lot of factors that go into this.
Mm-hmm. And do you have a suggestion about a good place to find that data for people who are working around the world?
Well, yeah, I mean, that's, you know, some of the sites, I'll send out some links to some sites that can give some ideas. But you know, in terms of future projections, the uncertainties are going to be they're huge. You know, and again, it's using the variety of methods that I had kind of outlined to try to get a grasp of what the range would be.
Mm-hmm. Great, thank you so much. I think we might have time for one more question, and maybe this one is for you, Christoph, just to clarify. Is the 2080 weather data available as EPW files?
Yeah, so that it is available. So effectively what you do, you load in an EPW file and that spreadsheet spits out a new EPW file. So it's extremely convenient.
Okay. And that's one of the links that we'll include when we let people know about the links that Russ talked about as well. We'll just describe where you can get that conversion spreadsheet for your EPW file that's existing, and then it converts it for you. Okay, well, thank you so much, everyone, for joining the webcast, and thank you to Russ, Chuck, and Christoph for taking time out of busy schedules to share your expertise with us.